Hello, welcome back. In this segment, I want to talk about one of the most fundamental theorems in number theory. It is called the prime number theorem, which deals with the distribution of prime numbers. How many prime numbers are there? How frequently primes occur? That kind of interesting questions, fundamental questions, which have many interesting applications in cryptography. For example, in public key cryptography like RSA and Diffie-Hellman, we make use of prime numbers a lot. So it's good to understand the fundamental mathematics behind prime numbers. Okay, so I wanted to focus on one particular question today. Okay, the question is, what is the probability that a given number is prime? Okay, this is an interesting question. How do we reason about it? So I'm going to explain the approach that I have been following for quite some time. Is this. Okay, suppose you have a number line like this. It's not really a line, but you can imagine it's a number line. And we start from numbers 1 through n. So how many numbers did we write? We write n numbers, 1, 2, 3, 4, all the way until n. Okay. Now I pick a number. Okay, I randomly pick a number and I ask, what is the probability this number is a prime? How can I answer this question? Okay, so it turned out that prime number theorem can help us to answer this question. So let me explain how. There are n numbers, so the denominator is clear. In probability, we need numerator and denominator. N is the possible number of numbers, right? There are n numbers. The question is, how do you find out how many numbers are primes? Suppose, let's assume we have a magic function that can tell us how many numbers are primes. So let's call that function magic function. I use the same notation the literature uses. Many papers in scientific literatures use this pi of n, denoting the number of primes from 1 through n, inclusive of n. Okay, so for example, if you take n to be 10, what are the prime numbers? All the odd numbers except 1 and 9. So we are left with 5, and 5 minus 2, 3. Okay, and we need to exclude anything else. What shall we exclude? We have to include number 2, because 2 is only even prime number. Therefore, pi of 10 is basically 4, right? Which we can easily check, because the numbers that are less than or equal to 10 that are prime are nothing but 2, 3. Let me write it here: 2, 3, 5, and 7. Okay, so these are the only prime numbers. Okay, so for n, we can imagine there is a magic function that will give us pi of n by n. Okay, so this is the probability for a particular number to be a prime. Okay, a number which is less than or equal to the n that we are given. Okay, all right. So the question now is, how do we find pi of n then? So it turned out that the prime number theorem has a nice approximation of pi of n, which I will show to you in a moment. I will not prove the correctness of that. It requires a little bit of mathematics, but we will make use of this fact as a fact. Okay, pi of n is actually approximated as n over log n. Okay, I will convince you by examples. I will run some programs and show to you that pi of n actually is pretty much same as n over log n to the base e, the natural logarithm. Okay, which means now we can go and plug this pi of n over here. So the probability formula can be rewritten as follows. Probability is nothing but now pi of n, in the place of pi of n, I can replace it by, I'm going to use equal to, but it's approximately. Okay, n over log n to the base e, right, which is again divided by n, right, because there is a n over here. Okay, so this n and this n will cancel out, so we get a probability of 1 over log n to the base e. So this is basically the probability. That means if you increase the n further here, the probability of finding a prime will go down on average. Okay, because the n is in the denominator. Okay, so we have this very nice model here, which helps us to reason about how frequently primes occur. So we can even say like this: on average, 1 in every log n numbers in this list of numbers is likely to be a prime. Okay, that's basically the important conclusion of one of the important conclusions of prime number theorem. Okay, all right, so I need to give some empirical sort of experimental data for you to show to you that pi of n is approximately same as n by log n to the base e. So let's get some programming going now. So what I'm going to show to you is the fact that first, let me show you the very basic function that we talked about earlier. This is a little program that checks whether a given number n is prime or not. Okay, as I mentioned earlier, I in fact proved it here that you don't need to go more than square root of n to check whether a number n is a prime. If n is a prime, you will not find any factors at all, of course, other than 1 and n. If it is a composite number, it's enough to stop until root of n. That's basically what we are doing here. Okay, so this program is something that I have mathematically proved. The theorem behind this this particular part, this is the part where it checks whether the factor I below square root of n, that's the reason I'm multiplying I 2 times. I into I means I square less than or equal to n means I less than or equal to root n. I check whether any I divides the n. Okay, if it is, then it's not a prime. Otherwise, I increment and try until all the square root of n possibilities are exhausted. Okay, all right, this is not going to scale, but it's fine for our purpose. This is the is prime methodology. Okay, and what we need is a way to count how many primes are there until a given number n. Okay, so let's do that quickly. Okay, I wrote another little Python function for that, right? So this is self-explanatory. It's just basically keep calling is prime for all possible numbers from 2 to n. That's the reason I put n plus 1. And if it is a prime, it increments the counter. Otherwise, it returns the counter as it is. At the end, it returns the counter. So let's call the print cumulative prime count, okay, of say 10. Okay, there are only 4 prime numbers and it shows correctly. And let's increase the number now. Let's do 100. Okay, now you have to trust the program is correct. There are 25 prime numbers from 1 through 100 inclusive of 100. Okay, now let's try to approximate that with the theorem that I talked about. Remember, a number the number of primes less than or equal to given n can be approximated as n over log n, and I wrote that as well. So let's call the prime number theorem for the same input that we talked about earlier. Let's try for 100. The prime number theorem says there are very likely 21 primes. The actual count is 25. You see, it's getting very close. Now we can try more. Okay, prime number theorem says there are approximately 144 primes from 1 through 1000. But let's count it using our slow counter. Still useful. 168, which is not that far from 144. So as you can see, the prime number theorem is a very good approximation of the actual count. Okay, and there are a lot of interesting proofs out there, and I'm skipping the proofs. We are just making use of the facts as it is, but it's a good approximation for us. Okay, so what is the purpose of talking about it in a cryptographic context? We would like to know what is the probability a given number can be prime, and how do we found it? We already solved the problem earlier. We said on average, 1 in log n numbers will be prime. Okay, so how can we make use of that and reason about the distribution of primes? Okay, let's talk about it. So okay, so the important result we have seen is that 1 over log n to the base e is basically the probability a randomly chosen number not greater than n is a prime. Suppose you assume that you are working with RSA or something like that. We deal with very large number. Maybe I'm just making an example. Say n is a 1000-digit number, okay, which is not that off from the reality. So let's assume n is a 1000-digit number. So a 1000-digit number means we can approximate it by 1 over log 1000 is 1000-digit, I said. So 1000-digit means approximately 10 power 1000, right? That's basically the meaning of a 1000-digit number approximately, and base e. So because of the log rules, the 1000 will come in the front. So we have 1 over 1000, right, into log 10 to the base e, which Python can happily compute and tell you. And let's do that now very quickly. So we need log, I'm just typing the log e to the base, log 10 to the base e, which is about 2.3, which I'm multiplying it by the 1000 in the front to get 2300 approximately, which means that we need to, okay, that means 1 over 2003 approximately. Okay, so what does it tell us? It means that if you're looking for prime numbers of 1000 digits, we may have to try 2300 random numbers before we get a prime number. Okay, that's basically it. Prime numbers do occur, but the number of primes is actually going down. As you can see, the probability of finding primes is going down significantly, but they do occur. For the number size that we deal with, it should not be a problem. Okay, what is interesting now is that if you say, well, let me increase my security from 1000 digit to 2000 digit, well, in that case, here you'll have 2000, and then you have 2000. That means you'll have 2 times here. That means the denominator increases by two times. That means the probability is 1 over 4600. Okay, so you have to try more numbers before you find a large random number which is prime. Okay, that's basically the conclusion. Okay, I hope you find this useful. We will make use of this in primality testing later. Okay, thank you.